All right. So, I'm going to show you a bunch of things about this. Hopefully this will be helpful to you. In these first few, it gives you some letters and it gives you what the net force is supposed to be. We're going to do this one. And we have to fill in the letters so that the net force ends up being what it says. Like figure out what the missing forces should be to make this, to make the net force match what it says down here. So this one says the net force is supposed to be 60 to the left. And right now it's got 80 to the left, and we need to figure out what goes on D so that we can make the net force 60 to the left. So what should go on D?
On what?
On this letter over here in order to make the net force 60 to the left.
20.
20 is right. Yeah. You paying attention, Daisy?
Yeah, I'm doing the activity, opposing activity. I mean, opening.
Okay. Good.
Same thing.
That's good.
Sorry.
That's fine. So, okay, yeah, 60 newtons. No, I'm sorry, you said 20. I was reading it. 20 newtons. 20 newtons. That's a 20, I think. I can make it say actually 20. 20 newtons. There. Okay. So, yeah, 80 minus 20 is 60. And 60 to the left because it's in the direction of the larger force there. So, good. Now, it can't be going up or down. So what do we need to make E if the up force is 300? What do you say? 300, yeah. Because there has to be zero net force up and down so that it's not going up or down. It's only going left. Like if we had made this 200 or something, then there'd be a net force of 100 this way and 60 this way, so it'd end up going like that or something like that. And we'd have to do math with the triangles and the angles, which we could do that, but let's not. That's 20 that way, and that's 300 that way. Good. Well, I am going to show you a free body diagram of one of these things, I think. First, I'm going to show you a generic free body diagram. So, imagine you've got this thing. I guess this could be a book. I don't know. It's a cylinder or a rectangular prism. That's what I was going to say. That's sitting on a surface here. Every free body diagram you draw today is going to have gravity on it. All these things are on Earth, I guess. So they're all going to have gravity. Now, one rule for the free body diagrams is the arrow has to start at the object and go away from the object. And each arrow has to be labeled with the type of force it is. So I labeled my arrow with the abbreviation for weight, which is force of gravity. So this thing is sitting on whatever surface this is, pressing down on it with its weight. That's force of gravity, or gravitational force, however you want to say that. There is another force that kind of goes with gravity. You all remember the other day where I was pressing on the table and the table pressed back on me and hurt my knuckles? Ow. That's a Newton's third law thing. I was doing an action force and it was doing a reaction force, and they were balanced forces because my hand wasn't going anywhere. It's just pressing down. It's pressing back up with an equal and opposite force. That's exactly what's happening. Anytime anything is sitting on a table or whatever, I could bring my water bottle over here and set it there. It is pressing down with its weight on the metal surface here, and the metal surface is not breaking. Good job, metal surface. That makes it, since it's at rest, that means there are balanced forces there. If there were unbalanced forces, then either it would fall through, or if the table were pushing up harder than it's pushing down, which would be impossible, but if it were, then it would be moving up. I guess that would be one of them Flubber situations. You guys seen Flubber? No? Robin Williams? It's not a good movie. Anyway, that supporting force that is an equal and opposite reaction force to the weight or gravitational force of the thing pressing down is called normal force, and that goes like this. So you can see it's equal because the arrow lengths are the same. We have to draw our arrow lengths about. They're supposed. The length is supposed to be about proportional to the magnitude of the force, and you don't have to draw it for like 1 centimeter equals 1 Newton or anything like that. And my arrows are not exactly the same length, but about the same length means about the same force, and these are supposed to be equal, so that's fine. Like you don't have to measure. Anyway, normal force is abbreviated F sub capital N, like that. And all of your diagrams will have gravity, but that's the only guaranteed force that'll be on everything. Not all of them will have normal force, because not all of them will be being supported by something. There's some things where something is sitting on something, like a book sitting on a table happens, I think, 3 times, but it's different each time. And there's a couple of things where there's something hanging from something, and all those will have normal force because there's a surface that is supporting the weight of the object. So there's the weight, and then there's the supporting on those. And even fewer of them, I think, will have an applied force. So it'll say that somebody's pushing, and whatever direction they're pushing, I always say it's to the right for some reason. It can be whichever direction you pick. That is the applied force. You guys have F sub capital A, applied force for that. And that's only when it says somebody's pushing. If there's nothing that's happening side to side, if it just says that it's sitting there or they're just hanging there, then you don't need an applied force. What do you say? There's another force, one more. Only when it says so, include friction. So, friction over here. F sub F for frictional force. That's friction. And it'll say include friction if there's supposed to be friction. The reason it goes this way is because if there's somebody that's pushing this book or refrigerator or whatever it is this way, if there's more friction, like imagine either this is like a concrete surface or this is like carpet or something. There's going to be more friction across the carpet. So if they're pushing this way across the concrete, there's not going to be very much resistance force. But if you're pushing on the carpet, that's going to be really difficult. And imagine it's a refrigerator. I guess that's what I'm doing. So friction works opposite the way that the thing is trying to move. If you're pushing it across the carpet this way, friction is pushing really hard back the other way, and you've got to overcome that force in order to get it to go. So that's why friction is in this direction. Friction is always opposite from applied force, and friction's only there when it says to include friction. Applied force is only there when it's being pushed side to side, pushed or pulled, whatever. Normal force is only there when it's sitting on something or being supported by something in another way. And gravity is always there. So I'm going to do this number 4 here, and then I'll show you number 7 and 8 also, I think. Am I really going to do number 4?
Perhaps.
No, I'm not. Okay, I'm going to do number 7 and 8. 7 and 8. Yes, sir. Okay, number 7. A rightward force is applied to a book. So here's my book. Here's my rightward applied force. They've all got gravity. And this book is sitting on a table, and the table's supporting it with the normal force. Keep in mind I made these arrows about equal. Because they're opposite and equal, normal force and gravity. Number 8, a rightward force is applied to a book in order to move it across the desk. So I got another book on a desk, got an applied force, it's sitting on the that book is heavier than that other book apparently. I didn't really mean to make that arrow so long, but whatever. Okay. Is it about the same? I guess. Okay. You know what? I better make these arrows about the same as they were before. Otherwise, that's not going to work out very well. Well, why don't you write that where they can read it, Mr. Franklin? Okay, there. So these things are exactly the same thing that's happening. But this one says, in order to move it across the desk with a rightward acceleration. They both say to consider friction. This one doesn't say move it across the desk with a rightward acceleration. It says move it across the desk at constant velocity. Okay, so this one has an acceleration, and this one doesn't. This one is keeping the speed the same. Interesting. So the difference between these, the thing that makes this have an acceleration and this one not, the way that we can make it have an acceleration and this one not, is with this frictional force that we have to include. Because right now they're both going to do the same thing. So if I make this frictional force real small, then because this force is much bigger than the frictional force and the forces are more unbalanced that way, this one will have an acceleration because it has a net force to the right. Whenever there's a net force, there's an acceleration. So if I'm trying to keep this one at the same speed, excuse me, I'm sorry. I don't want it to accelerate. It's supposed to be constant. You like that? What do I do to this one in order to keep it from accelerating?
Make an angle that way, the same amount.
The same amount as what?
The one going that way.
Yeah. I've got to make my frictional force about equal to that one. And like I said, you don't have to measure, but I clearly didn't try real hard to make this one the same as that one. So this one has a rightward acceleration. This one's constant velocity because I'm only applying just enough force to overcome the frictional force, but not enough to accelerate. Now, don't go putting all these arrows on every picture. They all have gravity. Make sure they all have their labels too. You need the arrow and the label. Don't need to make up numbers today. Just put the arrow and the label on there. You can make up numbers if you want to, I guess, as long as it's got the label on there. So they'll all have gravity. They only have normal force if it's sitting on a surface where the surface has that reaction force that's supporting the object. It pushes down with its weight, and the table or whatever pushes up with the supporting force. They only need an applied force if they're being pushed, and these might be the only ones that are being pushed, TBH, honestly. But only put friction if it says to put friction. And friction always goes opposite the applied force. Or if gravity is the only force and it says to include friction, air resistance will go opposite gravity, so it'll go in the other way. But if it's falling, remember there's no normal force because it's not sitting on anything.